right? So theta, it's like big O, but it means it's bounded below and it's bounded above by some constant, right? You need to know, have you guys learned theta already? Did you learn this sentence? If you learned it, you probably didn't understand it.
It's kind of between omega and big O.
It's both of them.
It's
both omega and big O. Did you guys learn it? Did you learn this stuff, this sentence here, this logic?
Yeah.
Try to write it on the board. Let's go through and see what it means.
I don't remember.
Yeah. Probably if the professor was bold, she wrote it on the board, but knew you wouldn't understand it. So let's see if we can understand it, because this is logic course. You need to be able to understand logic sentences. So what are we saying? We're saying we have two functions, f of n, right? Here's a plot of f of n. As n grows, f of n grows, right? And it wiggles around. That's f of n. And what's g of n? G of n is this nice smooth function that we understand, right? And what we want to do is we want to say that f and g somewhat have the same general complexity. G is well behaved, so we like G, but more or less G and F are going to grow in the same sort of way. What does that mean? Well, when you don't care about the multiplicative constant, they grow in the same way. So we're going to say that F is always bounded between one constant times G and another constant times G, right? Oh, this one down here was our G. I pointed at the wrong, your faces were covering it up. This one down here is G. This is G times one constant. This is G times another constant, all right? And we're saying F is always between those constants. Well, always is a little, it's not between them down here, right? Everybody following that? All right, so then you might say, yeah, but which constants? Well, I'm claiming that there exists constants. All I need is show you some constants for which it's bounded between, and I'm happy, right? So what's my C1 going to be? Well, my C1, all these constants have to be finite and bigger than 0, all right? Whenever I say a C, assume it's constant and bigger than 0. So here, 0.000001, that's a constant bigger than Z. And C2 could be a billion. That's a constant bigger than, right? It's finite. And so I'm going to say F is bounded by this. It's always bigger than this really little number times C, and always less than this really big number times C, right? So I get to choose, when I'm trying to say that F is theta of G, I get to choose what the constants are. All right, that's good. Now, for which n? I didn't say n here. Well, for all n that are sufficiently big, right? Because what do we care about when we talk about how fast the function grows? We care about its limit as n goes to infinity, right? So we're saying for every input that's sufficiently big, it's going to be bounded, right? All here in the picture, it's bounded between those two for all sufficiently big n. All right? All right, but what's my definition of sufficiently big? Right down here, n's too small, so it's not true. Well, I don't care. You can give me any definition you want of sufficiently big, right? Here, I'm n naught. We call this n naught. It's my definition of sufficiently big. So I get to come up with the lower bound constant. I come up with the upper bound constant. I get to say what I mean by sufficiently big. And then the adversary comes in and says, okay, great. for every n that's bigger than your sufficiently big, f has to be bounded by your constants. Right? Does that make sense?
Very quick question.
And
Yeah.
How do you know? Sorry, how do you know if it exists C1 and C2, or if it's for all C1 or C2?
Well, because this is the definition of being bounded, right? It's not bigger than 1 times g, so it's not a for all. I'm saying there's some constant it's bounded. It's bounded by 5 times g. It's not bounded by 1 times g.
Okay.
Right?
and
Yeah.
go back, please. And C1 and C2 are both different because
One
they're
is
both
bounding
like
from below and one's bounding from above.
and C1 and C1 and C2 are like they're like different. They're like different numbers because
C1 is likely 0.001 and C2 is likely 1,000.
and G of n, they're both the same function, just their constants.
Which
Making G of n is the
is a
same function.
Is a function.
Yeah, it's
Here
the
it
same.
is. This function here that's growing. Let's
Oh
do
yeah,
an
and then
example. Let's do an
I
example.
understand. I understand.
Sorry?
Yeah, because
Here, suppose the running time of your algorithm is 8n squared plus 1,000n, right? And your boss comes to you and says, what's the running time of your algorithm? And you say 8n squared plus 1,000n. Do you think he cares? He doesn't want all that detail, right? He wants to know, is it big O of n squared, right? This here is saying it's big O of n squared. It's bounded by n squared times some constant, right? Your running time is big O of n squared. I should have that in there. So how do I do it? How do I prove it to your boss? I'm going to prove to my boss, that to the adversary, that the running time is big O of n squared. Well, it's my algorithm, so I get to say what the running time is, right? I'm saying it's bounded by 9 times n squared, as long as your n is bigger than 1,000, right? If your n smaller than 1,000, I'm not making any claims. But, right, why did I make c to be 9? Well, I need it to be bigger than 8, and then I got to eat this somehow, right? So I made it 9, right? The 9 is big enough to, the 8 gets this, and the extra 1 n squared is going to beat that. All right, so let's prove it. Now, so I came up with these constants, and then the adversary comes up with a really, really big n, right? So let n be an arbitrary number that's bigger than my 1,000, right? So it's an arbitrary, sufficiently big number. Then we have to prove this. How do we prove it? Well, the running time is 8n squared plus 1,000n. That is actually equal to 8n squared plus n squared. Sorry. That's less than or equal to why? Well, the 8n squared we just got there. Well, because n is bigger than 1,000, 1,000 times n is smaller than n times n, right? Everybody buy that? Let's compare 1,000n to n squared. Well, n squared, here you divide through by n, and this is true as long as n's bigger than 1,000, right? So the extra n squared I put in here is enough to eat up the 1,000n, right? As soon as n gets to be bigger than 1,000, n squared is going to eat up 1,000n, which gives us 9n, which gives us what we want. Everybody buy that?
Sir?
Yeah.
Sir, can you go back to the previous slide if it's possible?
Yeah, of course it's possible. Anything's possible.
I did not understand what we are supposed to understand from this slide yet. So I was.
All right. Well, let's do this slide instead, because it says the same thing.
Okay.
All right? I want to prove to my boss that my algorithm runs in what we call order n squared, right?
Yeah. Okay.
And what does that mean? It means for sufficiently large n, right? I'm not claiming, right, when n is really, really little, right? Suppose n is only 1. Then c times 1 squared isn't much time, right?
Yeah. Yeah. It's
So I'm
safe.
not claiming my running time is good for really, really small inputs, because I gotta do some initial setup, right?
Yeah.
I'm saying for all sufficiently large n, it runs in order n squared, right? And what does that mean? That means there's some constant such that the running time of my program is bounded by n squared, right?
Yeah. Okay.
Right. So how do I prove that to my boss? I have to. I'm claiming my running time. This is my running time. My running time is, in fact, 8n squared plus 1000n. Right. But that's too much detail. Right.
Yeah.
The way you do big O notation is you drop the low order terms. Right. So here, which is bigger, the n squared term or the 1000n term? Well, the 1000 looks scary, but you should know that n squared always dominates n.
Yeah.
When n gets big. Right?
Yeah.
Why is that? Because here we can prove it right here. Here we got 1000n, and here we got n squared. Right?
Yeah.
Which one's bigger? Well, when n is small, the 1000n is bigger. Right?
Yeah. Right.
And n equals 1, you got 1000 times 1 versus 1 squared. Right?
Yeah. Okay.
But when n starts, but what we care about here is big N, right? And when n is 1,000,000, 1000 times 1,000,000 is a lot smaller than 1,000,000 squared.
Yep.
Right?
Yeah.
In fact, where's the cutoff? Where's the point where it switches? Well, here, if you cancel off an n, you get that 1000 is less than or equal to n. Right?
Yeah.
So n squared starts to win when n gets to be 1000. Right?
Yeah.
So
Like as n gets bigger, n squared is bigger than n, right?
yeah, exactly. Yeah. Right. So I know that my program is a little sluggish for inputs of the size of 1000. Right? But I know that my boss's algorithm, all his inputs are the size of 1,000,000. Right?
Yeah.
So the fact that I took a little time setting up, he's not going to care. Right? So I'm going to say, yeah, boss, as long as you give me inputs that are bigger than 1000, the running time will be at most 9n squared. Right? That's what I want to say. Right? I want to say there exists a C and an N naught. Well, which ones? 9 and 1000. Okay, they exist. Here they are, 9 and 1000. And then what's true for those? What's true is if you give me any input for all inputs of size n of any n that are bigger than 1000, then my running time, here's my running time, 8n squared plus 1000n. I claim that's bounded by 9 times n squared, right? And then
yeah.
prove that. Here, 8n squared, 8n squared. Those are the same. 1000n, well, that's dominated by n squared, right?
Yeah.
So then 8n squared plus n squared is 9n squared, which equals to the C that I had in mind.
Yeah.
Right?
Sir.
So my boss is happy.
Yeah. Sir,
Right.
so being bounded by 9n squared means that whatever I use, like the runtime, the time will be like around cn squared, right?
Yeah.
Okay.
Yeah, so I would just say, my boss would say, would I do this, say all this to my boss? No, I would just come in and say, hey, boss, the running time is n squared. And it's not n squared. It's 8n squared plus 1000n. But he knows that I don't care about constants, right? He
Yeah.
knows when I say n squared, I really mean order n squared. And he knows that when I say order n squared, I mean it's times some constant for sufficiently large n. He knows that,
Yeah. Okay. Thank you. Yeah.
right? Because he took the same course that we're taking now.
Jeff,
Yep.
is there a process where you go through to choose your n naught for like for every general like functions to decide big O?
You know, everything is undecidable here. So is there a process? I don't know. I try to give you processes, right? So I would say in this case, right, we need a C that dominates the 8, right? Here's an n squared, so C definitely has to be bigger than 8, right? Now I have to eat up this stuff. And I have a choice. I could make C be, what happens if C was 1008, right? If C was 1008, then n naught could be 1, right? So there's a trade-off between the C and the n naught. It's not even a unique answer, right? People see that if I made C be 1008, then this is true for every n bigger than 1. So as long as then I would make n naught be 1.
Does it depend on your algorithm though? Like n naught, does it depend on your algorithm or is there any
My algorithm is 8n
8n
squared
squared
plus 1000n, right? So so we could say really the running, for big N, the running time is 8n squared. But somehow there's this initial setup of 1000n, right? How do I pay for the 1000n? There are two ways to pay for it. I could make the C bigger, right? I make the C 1008, right? Or I could make sure, or I could say C is 9, which in some ways the boss is going to be happier with a constant of 1000, a constant of 9 than a constant of 1008, right? So we make the constant 9, and then what do I need my C naught to be? Once I've set, how did I do it? I made it as 9 because I needed it 8 and I needed it bigger, right? So what is 9? 9 is 8 plus 1. That's how I got 9, right? I knew C had to be bigger than 8 to eat this, and I needed to eat this somehow. So I just made C 1 bigger.
So
right?
100 would also be the right answer though, right? Because it's still bigger than 8.
C could be 100.
Right, okay.
Right?
That's anything that's bigger than the thing on the left.
Anything bigger than 8 would have worked here, right?
Okay.
And then once you had your C, then I have here, I chose 9. So here I have 9n squared. And then here I have 8n squared plus 1000n, right? So I need to have that this is bigger than that. Well, it's only bigger for sufficiently large n. So then what did I do? I canceled the 8n squared with the 9n squared, and I got n squared, 1n squared. And then I said, when is 1000n? When does n squared dominate 1000n? It dominates 1000n when n's bigger than 1000, right? And that's why it shows n naught to be 1000. Right? Does that make sense?
Right, and n naught also depends on C.
Yeah. Yeah, there's a playoff between C and
Sorry,
9.
n naught depends on C, right?
Yes.
Right, so if you
Yeah.
change C, then n naught, if you make C higher, n naught will be lower, and if you make C
Yes.
lower, n naught will be higher.
Yes.
Okay.
Right? For example, if C was 1008, then n naught could be 1. All right, so now we're saying we're doing it for exponential time, right? Here I want to say my running time is bounded by an exponential. How do I do it? I say, well, I let all right, well, here I'm just making them really big. I don't know why. Oh, here. Oh,
Could you take the log and then the numbers would be smaller?
yeah, here. Here's the question. Suppose my running, now I got what we're doing here. My running time is n squared, right? And I'm going into my boss and want to claim to my boss that my running time is bounded by some constant times c, right? Everybody get that? And that's false, right? This is a false statement. N squared is not bounded by a constant times c, right? So how do I go into my boss and I want to prove to my boss that it's bounded? How do I prove it? I come up with some c that's and some n naught that are really, really big, right? Maybe if c and n are really, really, really big, I can win here. So I met them big. And then the adversary comes up with the end, right? What do we need the n to be? Well, he comes up with an n that's bigger than my c. I come up with a bigger and bigger c. He comes up with a bigger and bigger n. His n better be bigger than my n naught, because that's the requirement, right? N has to be bigger than n naught. And we'll see later, I also need my n to be bigger than 3. All right? So here, right, if I'm trying to prove this, I come up with this c and an n naught, and the adversary comes up with a bigger n. Now let's see who wins. Well, 2 to the n is bigger than n squared for every n bigger than 3, right? If you plug in here 3, you get 2 times 2 times 2 is 8. You plug in 3 here, you get, here I did it. 2 times 2 times 2, 2, 4, 8. Oh, I guess I got it wrong. Here's another bug. Let's change this to 3. Well, it was 3 before, right? There, 4. Now, 2 times 2 times 2 times 2 is 16. Oh, let's change it to 5. Okay, here, I'm really hurting you guys. All right? 2 to the 5 is bigger than 5 squared. That we got, right? Everybody with me here? N squared is bigger than 2 to the n is bigger than n squared as long as n is bigger than 5. So I made it bigger than 5. And then c times n. So then this is false, right?
Can you
And we know
re-explain
that n
about
times n squared is bigger than c times n. Why? Because I made n bigger than c.
So anything under 5 wouldn't work?
Yeah, exactly. Right here, 4, 2, 4, 8, 16. 4 squared is 16, so it's not bigger. Right? So when I say n squared is bigger than 2 to the n, well, that evidently doesn't kick in until n is 5. Right? I naively stuck in 3, but it didn't work.
Jeff,
Everybody good with that?
so you know how, like you said, let C and N all be arbitrary.
Right.
But over here in the quantifiers, they're existential. They're not universal for them to be arbitrary.
Yeah, but I'm trying to prove it's false. Right?
Also, you're contradicting. So
Yeah.
you're saying the opposite. So you're saying
Yeah.
that.
Yeah, right. So over here, the prover was so confident in that he could play the game and make this statement true, right? He can come up with the C and an N naught. And he was thinking this is really great. So the next day, he had a program that ran in 2 to the n time, and he's trying to do the same thing, right? He's trying to prove that this is true. So how does he prove that it's true? He comes up with some C and some N naught, and he makes them really, really big. Why? Because he's nervous. He's somewhere in the back of his mind. He remembered that he learned that exponentials are bigger than linear. So he thought, well, maybe if he makes the C here, if we make the C really, really, really big, maybe we'll be good, right? So he makes C be some big number, and he's hoping that his boss will be happy, right? He says, boss, my program runs in at most 1 billion times n, right? So then the adversary says, no, it's not true. I can come up with an n on which this is going to be wrong, right? And what does n have to be? Well, as C gets really, really big, I make a bigger C, I'm going to need a bigger n to dominate this, right? I want to prove that my blue friend is wrong. I'm red. I want to prove my blue friend is wrong. His running time is n to the n. It's not C times n, right? But as he makes the C bigger and bigger and bigger, right, then he's making this sentence more and more true, right? Because C's big, this becomes bigger. So how do I beat him? I have to make this bigger. How do I make this bigger? I make my n be bigger than his C. He gives me a C of 1 billion, I give my n 1 billion. He gives me a C of billion, I make my n 1 billion. Right? All right, now I also need the n to be bigger than his n naught. And as we've seen, I need my n to be bigger than 5, right? And now I'm going to prove that he's wrong, right? The running time of his program is n 2 to the n. Well, that's bigger than n squared for every n bigger than 5, right? Now, why do we call about n squared? We don't care about n squared. We care about c to the n. It's c times n, right? Well, I know my n is bigger than c. So I know n times n is bigger than c times n, right? And so now I proved that this statement up here is false, right? People buying that? Right?
Can you
If you think
explain
everything
about that?
we've been doing in this logic course is not useful, this is first year material about knowing that this program runs in n squared time, and this program does not run in linear time. Right? Does that make
Can I
sense?
ask a question? Yeah.
Of course you can.
Can you explain about the second speech bubble? Let n equals max Cn. Like, I don't
Yeah.
get
I
what
want to
you're
make,
saying.
my goal is to prove this sentence false, right? What is this sentence saying? It's saying for every sufficiently large n, he's claiming his program doesn't take longer than some constant times n. That's what he's claiming, right? And in order for him to claim it, he's given me a really big C, right? Maybe he's given me a big n naught. I don't know. So how do I prove he's wrong? He's saying it's true for every n. So I come up with one n which it's not true, right? And what do I need my n to be? Well, I need my n to be, I need to make it big to make it true, right? The bigger the n is, I'm claiming the bigger n is, the more wrong he will be, right? So if I come up with this a really, really big n, then he's going to be wrong because 2 to the n is going to start really dominating c times n. So how big of my n do I need it to be, right? Well, I need my n to be bigger than his c because if he makes this really c big, then that's going to be, if I make n to be 1 and he makes his c to be 1 billion, he'll win, right? So if he makes his c to be 1 billion, I'm going to make my n to be 1 billion, right? That's fair, right? I also need to be n to be bigger than n naught. Why? Because we're promising I have an n that's bigger than n naught, right? And I'm never going to make my n smaller than 5, right? So if he's fair and says c is 2, then I'm going to still say n is 5, right? Why? Because n is the biggest of all of these, right?
That sentence simply says that n is going to be bigger than c in n0 and 5.
Yeah. Yeah, it's
Okay.
the maximum of them,
Okay.
right? I wanted n to be bigger than each of those, right? And if n is bigger than 5, then 2 to the n is bigger than n squared. And if n is bigger than c, then n squared is bigger than c times n, right?
So you want it to be at least 5.
Yeah,
If not
I want
greater.
it to be at least 5 for this greater than here, right?
Okay.
Right, because if c is 4, 2 to the 4 is 16, and 4 squared is 16, so it's not bigger, right? That's why I made it bigger than 5.
Sir,
Yep.
so we wanted to show that the relationship was false for
Yeah.
n bigger than 5, right?
Yeah.
So since 2 to the power n is bigger than n squared for n 5,
Yeah.
this thing is false, right?
Yeah.
Since that is true. Okay.
Yeah.
All
Yeah.
right.
And,
Okay.
and you can see it's true for 5, and then play around a bit. You know, if you know anything about calculus, you know anything about plotting, right? The derivative of this is always going to be the derivative of that, right? So for even bigger n, it's going to be even bigger. Right? Everybody buy
Yeah.
that?
Yep.
Sorry, can you explain that again? The derivative of what is the derivative of?
Do you know, do you buy that? Plug in 5 here, and you get that this is true, right?
Yeah.
Now, are you convinced it's true for every n bigger than 5?
No.
Oh, well,
Oh, sorry, bigger than 5. Sorry, I thought you said any n.
no. For any big n bigger than 5, this is true, right?
Yeah.
Yeah, that's all I'm saying. How would
Okay.
you prove that? I don't know. I would use calculus to prove it, but I don't know. Right? Everybody good with that? All right. So here's another sentence. You know I like throwing in various sentences. So everybody study this sentence. It's a good sentence to put on a test. Is this sentence true or false? Right? It's saying that 2 to the n is less than c times n. Is that true?
I think it's
Is it
false.
false?
You think it's false? Anybody think it's true?
Yeah, it's true. You can always take the c that'll be bigger than n. The c will be huge.
Exactly.
It's
Order
true.
matters here, guys.
It's true.
Right? This is true. How we play the game. Let n be really, really big. Right? Okay. You gave me a big n, but I'm going to give you a bigger c. Right? You give me n, I'm going to let c be 2 to the n. Now, it's true. So we're done. Right? My c can't depend on my n. Right? I need to come up one c that works for every n. I can't have my c grow with my n. If c, it goes back to what I've been saying a billion times. I want one c that works for every n. Here I'm saying for every n there's a c. So my c is a function of n. Right? Can my c be 2 to the n? There, c is a function of n. If c equals 2 to the n, then this sentence is true. Why? Because 2 to the n is less than or equal to 2 to the n times n.
Isn't 2 to the n times n 2 to the n plus 1?
It is, but all I needed is that it was bigger, so I didn't get
Right.
worked up about it.
No, I just mean like it's easier to show if the exponent's larger, the base is the same. Then you could just say n plus 1 is larger than n.
Sure. As long as n is bigger than 1, right? Right, people follow this? This is our first order logic stuff that I'm really hoping by this late in the term you guys can follow. Right? Now just to complete it. Theta means that it's bounded above and bounded below. Big O means it's bounded above. Omega means it's bounded below. Little o means that it's shrinking. It's really it's really smaller than G. And the little omega means it's really bigger than G.
Sir,
Yep.
is this the computing slides? Like, which the topic name? What is the topic name for this slide?
Computing.
Computing, right? Okay.
Yeah. It's the next slides on the web page.
All right.
Jeff,
Okay.
we in our last courses we learned theta, big O, and omegas, but not little o or little omega.
It
I never.
means the ratio. If you take, it says G's bigger. So if you take G and you divide it by F, then as N gets bigger, G divided by F grows. It's bigger than any constant. And this means that if you take G and you divide it by F, then it shrinks. The limit goes to 0.
Okay,
Right?
I see.
Right? Take F and divide it by G, the limit goes to 0. Take G divided by F, the other one, F divided by G, the limit goes to 0. All right. We're running out of time, but let me finish up this classifying functions, right? This is just saying it's polytime, right? Why is it polytime? It's because we've said this already. It's a review, right? 3n squared plus 7n plus 8. It's a polynomial. Why? Because it's bounded above by 4n squared, and it's bounded below by 2n squared, right? What about this? 3 to the n times n. Well, again, we can play with it and see it's bounded by 2 to some constant times n, right? And that, this is just coding phase versus, we did that already. And now we're done time complexity. All right? I had this fantasy we were going to cover so much material today, but it seems we're still just struggling along. Are you guys understanding this logic? Sounds like you're still struggling with it.
No, I mean we're getting to the point, we're getting to the logic, but at the same time, maybe just looking some other ones over, maybe that'll definitely prepare us for the next upcoming test, the last one.
I'm not
Yeah,
trying to
definitely.
prepare you for
Exactly,
the next
yeah.
test, dude.
More practice.
I personally
Yeah,
don't
more
care
prep.
about the next test. I care about your computer science degree, right? You need to be able to understand big O notation, right? And the definition of it is this. So this kind of stuff comes up in computer science a lot, and it's good to understand it. All right?
I
Yes.
think more practice questions would be great.
On complexity practice questions?
Yeah, I mean, like classification or similar practice questions that we were just doing with the 2 to the n and
Well,
squared plus
Yeah,
1,000
those
or
practice
something.
questions help.
let me tell you, if you want so much, you come over here to, where is it? This course? Oh, not that course. That's you. Let's try this course. Not that course either. Let's look around. We'll find you some slides. Let's go over to third year course. Slides here. We've got, what's this? This is intro. This is running time. So here's a set of slides on running time. You can look, those are running time slides. You can see they're 2011 running slides. So if you want a whole thing on running time, That might be good to look at. And then here, first order logic game. I think maybe those. Oh, that's 1090. Somewhere, I can find it. I was trying to prove to people this big O notation, and so I was doing more and more slides. And no matter how many slides I do, people claim they don't get it. But if you want more slides on big O notation, I have thousands of slides on the topic. Maybe not thousands. How about 100? I bet you I have 100 more slides on this topic. So I could find them if you wanted. I just don't know where they are right now. Oh, what's this dot down here? Math, there it is. Look at that. See, it says 3101 syllabus, math. Let's download that and see what we get. Is it down yet? Is it open yet? How many slides we got here? Woo. 421 slides. And what is it covering? Oh, well, it's covering a bunch of things. It's covering here. These are all slides on big O notation, right? Sums. Here's if you want to classify problems, right? We got polytime, exponential time, right? We can think about how do you bound sums. Here, let's start at the top, right? What is it? The time complexity of classifying functions, right? How to sum up things, recurrence relations, more details. So if here we go to classifying functions is what you asked for. And we got so many, right? Here we can classify it as constant or logarithmic or exponential, polynomial. Here we can classify more. See, I just got lots of slides here. Here's more examples. I don't know, maybe even this is, I don't know. Or maybe I put more down here. Anyway, I got a lot of slides if you want more slides. Oh, here's more. Here's more down here. I threw in the bottom. All right. Here's a lot more slides on the topic, right? Which is bigger, this or this or this or this, right? So here's more examples of classifying functions, right? See, I've been a slide making addict for decades. I need to go to a meeting and say, my name is Jeff and I'm a slide making addict, right? So here's more examples, right? You want more examples? Here are more examples, right? Here's more examples. So many examples. Trying to get you guys to understand it. Do you know what I say? I've been teaching this stuff for 25 years and you still don't get it. That was a joke. Did anybody laugh?
I laughed.
I laughed.
I also laughed.